Hi guys. So today let's continue with our discussion on Asian options. Today we're going to discuss how to come up with a partial differential equation for the price of a Asian option using change of numeraire. So on the x-axis, let's assume that we have time. On the y-axis, let's assume that we have the value of the stock. The stock basically starts at S0, and let's assume it basically undertakes a path like this. This basically is our expiration of the option, which is time capital T. Now let's assume that there is a constant C. This basically is C. So this point then becomes T minus C. Okay. So for the discussion today, we're basically going to consider a Asian option where the average price for the payoff is going to be the average the stock price takes between this time period. Okay, so we're now going to consider the entire time period for the payoff of the Asian option. We're only going to consider the average value taken by the stock in this time period, and we can write down the payoff of an Asian option as let's figure out what the average here is going to be. Average is going to be given by integral T minus C to T S of u d of u, and since this length is equal to C, we have to divide it by C. This basically would give me the average stock price in this time period, and I need to subtract the strike price and take the maximum of this and 0. Okay, so this basically is my payoff of a Asian call option. Now if we basically assume that C is equal to T, okay, then this basically is the same payoff that we talked about in the previous lecture. In that particular case, we basically consider that we take the average over the entire time period. Okay, if C equals to T, then we're taking average from 0 to capital T, and that would be the same payoff as the last lecture. Okay, so in order to basically compute the partial differential equation, what we're going to do is we're going to create a replicating portfolio. And in that replicating portfolio, we're basically going to take a position in the risky asset, and here the risky asset basically is the stock, which is modeled as a geometric Brownian motion, and we're going to take a position in the money market account. Okay, and for this discussion, we basically are assuming that the interest that we get in a money market account is constant at R. Okay. So let's basically see how we basically are going to construct a replicating portfolio. So we basically want that the replicating portfolio at time capital T, the value of the portfolio should equal 1 by C integral T minus C to T S of u d of u minus K. Okay, so this is what we want. So whatever replicating portfolio we create, we want the value of the replicating portfolio at time capital T to be equal to what's inside this bracket. Okay, that's exactly what we want the replicating portfolio to be. And we basically are going to invest in stock and money market account. Okay, and let's assume that we have a non-random function of time given by gamma of t. So this basically is a non-random. It's important that this is non-random. It's a function of time, okay? And because it's a non-random function of time, we can basically write d gamma of t times d gamma of t is equal to 0. Because this is a non-random function of time, it would not have a dw term. In that case, the quadratic variation is going to be equal to 0, right? And if we basically model the stock as a geometric Brownian motion, then we can write ds of t times d gamma of t to be also equal to 0. Okay, so that's very clear because we only have a function of time and it doesn't really have any randomness in there. So the quadratic variation is going to be 0 and the cross variation is going to be 0 as well. Okay, and what we now want to do is we want to basically construct a portfolio where we're going to take this basically is going to this gamma of t is going to be the number of shares of the underlying risky asset that we hold at any point in time. So what we're going to do is if we have xt is the value of the portfolio at any point in time, we basically are going to buy gamma t, number of shares of the underlying risky asset, and the risky asset is going to be trading at S of t. So this is how much money we're going to invest in the risky asset, and the remainder money, which is going to be given by xt minus gamma t st, and this much we're going to invest in the money market account. Okay, and we're going to keep rebalancing this portfolio according to some trading strategy. Okay, and we basically then need to figure out what is the initial capital we need to start with and what this trading strategy is. Once we figure out what the initial capital is and what this trading strategy is, then we can guarantee that the value of the portfolio at time t is going to be equal to this. Okay, so that's what we want to do. We want to find out what is the initial capital and what is the trading strategy such that the value of the portfolio at time capital T would give us this. Okay, so then that's what we want to discuss next. We want to basically come up with a strategy and an initial investment that's going to give us the value of the portfolio at time t equals to this. Okay, hopefully that's understood. So let's move on. Okay, so in order to compute this replicating portfolio, let's look at a few differentials first. So I want to basically look at the differential of gamma of t times st. And as we just talked about, the quadratic variation of this function is going to be equal to 0, and the cross variation is going to be 0 as well. Hence, this can be written as gamma t dst st d gamma t. Okay, rest all the terms basically would go to 0. So let's call this result 1. Okay, now what I want to do next is I want to find the differential of e to the power of r t minus t gamma t st. Okay, and in order to compute this differential, this is going to be e to the power of r t minus t. I'm going to have a minus r gamma t st dt. Okay, plus e to the power of r t minus t, and differential of this, which is given right here, so I can take it from here, ds of t plus st d gamma of t. Okay, and here what I can do is I can basically I can simplify this a little. I have e to the power of rt minus t and a gamma t, and if I take this out, I have a gamma t here, e to the power of rt minus t here, so I'll get ds of t inside, and here I'm gonna get r st dt. So I've combined this term and I've combined this term. This is what I'm going to get. Okay, and then I'm gonna have this term remaining, which is going to be rt minus t s of t d gamma of t. Okay, so now I can write this as this is the right hand side, left hand side was this. So here now I can write this as er t minus t gamma of t ds of t minus r st dt. This is equal to d r t minus t gamma t st, right? And I can move this term on the other side. We'll get minus r t minus t st d gamma t. Okay, so this is another result. Let's call it result number 2. And I'm going to use this result a little later. Okay, so just trying to actually look at these differentials one after the other, and this result we'll basically use a little later. So that's what we're doing. We're basically just looking at these two differentials, and this is the result that we're going to get. Okay, so let's now proceed. So as I said, we're basically going to have a portfolio, and let's assume that the value of the portfolio at time t basically is xt. What we're going to do here is we're going to buy gamma t number of shares of the risky asset, and here the risky asset is a stock which is trading at S of t, right? So this is the amount of money that I need to invest to buy ST number of shares, gamma t number of shares of ST. So that's my investment in the risky asset, and the remainder money, XT minus gamma t ST, this would go into a money market account which is going to accrue interest at the rate of R, right? So now if I want to look at what is D of XT, now D of XT is basically going to have two components. One is going to be from the changes in the value of the underlying risky asset and the amount of interest that and the second position is going to be the amount of interest that my portfolio accrues in that dt amount of time. So this basically can be written as gamma t d of st plus xt minus gamma t st, and it's going to accrue r dt, right? This basically comes from my holding in the stock. This basically comes from my holding in the money market account. So dx of t is basically given right here. Now what I want to do is I want to compute d of e to the power of r t minus t x of t. Okay, and let's basically compute that. So this can be written as e to the power of r t minus t. Then I'm going to have a minus r here, x of t dt, plus e to the power of r t minus t dx of t, which is going to be right here, gamma t ds of t plus xt minus gamma t st r dt. Okay, so that's what I'm going to get. Now if you look at, I have minus r xt. Here also I have xt here, r xt. I have a minus r xt. Then I'm multiplying this by e to the power of r t minus t. I have a e to the power of r t minus t and dt. So this term, this is negative and this is positive. So this basically gets cancelled out. Okay? So these two terms cancel out, and what basically is left on the right hand side, I basically will get, and I can take this gamma t outside the bracket, so I'll get e to the power of r t minus t gamma t, and I'll be left with ds of t minus s of t r dt. Okay, so this is nothing but d r t minus t x of t. Okay, so let's call this result number 3. Now if you look at result number 2, we just basically computed that e to the power of r t minus t gamma t times d of st minus r st dt r st dt. This is equal to this thing on the right. So what we can do is we can, instead of this here, we can substitute this. So then we'll get d e to the power of r t minus t x of t is equal to this, d e to the power of r t minus t gamma t st minus e to the power of r t minus t st d gamma of t. Okay, so we get this result, and let's call this result number 4. Okay, and we're basically going to use this result to compute the value of the portfolio at time capital T. Okay, in just a moment. So just remember that we basically got this result 4, and we're going to come back to it in just a moment. Okay, so as I said, what we want to do is we basically want to come up with a replicating portfolio such that the value of the replicating portfolio is equal to this at time capital T. And what we need to do is we basically are going to create a replicating portfolio using the risky asset and the money market account. But what we need to do is we need to find out what our trading strategy is going to be, or in other words, we need to find out how much of stock we're going to hold at each point in time, and we need to know what is the initial capital we're going to start with. Okay, so once we know what is the initial capital, and once we know how much stock we're going to hold at each point in time, okay, then that basically would give us the replicating portfolio, and we're going to choose these two such that the value of a portfolio at time capital T equals to this. Okay, so that's what we want to do. So what I claim is that gamma T is equal to 1 by RC 1 minus e to the power of minus RC, okay, when time is 0 is less than equal to T, less than equal to T minus C, okay, and gamma T basically is equal to 1 by RC 1 minus e to the power of minus R T minus T, okay, when T minus C is less than equal to T, less than equal to capital T. Okay, so this is what I'm claiming. I'm claiming that when time is less than equal to T minus C, this is the number of shares of the risky asset that we need to hold. And when time is greater than T minus C but less than T, and during that time period, this is the amount of stock we need to hold at each point in time. Okay, and I'm also claiming that x0, which is basically our initial capital, needs to be 1 by RC 1 minus e to the power of minus RC, which basically is the gamma T, okay, times the value of the stock at time 0. So at time 0, stock is trading at 0, and I need to hold gamma T units of that stock, okay, because time is less than T minus C. So this basically is this, and multiplied by the number of the value of the stock at time 0. And I'm not going to have enough money to basically buy the stock, and I need to basically borrow K e to the power of minus RT amount of money from my money market account. Okay, so what I'm claiming right now is, let's basically understand this carefully. I'm claiming that if I start with this much amount of money, or this is my initial capital that I invest, okay, and I basically at every point in time I basically buy this much amount of risky asset, okay, and I keep doing this till expiration, then I'm claiming that the value of my portfolio is going to be equal to, then I'm claiming then x of t is going to be equal to 1 by c integral t minus c to t s of u d of u minus k. Okay, so again I'm basically claiming that let's basically start with this initial capital, and we're gonna hold this much amount of stock at any point in time. Okay, and if I do that and I keep rebalancing my portfolio and keep moving between stock and the money market account, then the resulting value of the portfolio at time capital T would be equal to this. So that's what I want to show you next. Okay, so this basically is my claim, and I want to prove next that if I do this strategy, okay, this is my strategy, okay, if I basically do this strategy, then I will get this. So that's what I want to prove next. Okay, and in order to prove that, we're basically going to use this result that we got. Okay, so let's see how we can prove that if we do this, we'll get the value of the portfolio equals to this. Okay, so let's basically look at this graph once again. We basically, on x-axis we have time, this is our capital T, this is T minus C, and this basically was equal to C, right? This basically was our expiration of the option, and we basically are going to consider the average of the stock during this time period, right? Now, as I said, we basically are starting with this initial capital, so we're buying so many units of the stock, okay, according to this formula. We basically are starting with this many units of stock, and while t is less than equal to t minus c, just notice that the number of units of stock that we hold is static. It's not dynamic. It doesn't depend on time. Here you don't see any time. Okay, so whatever number of units that we are holding at the beginning of the time period, at time 0, we would be holding the same number of units at time t minus c, because this doesn't have any dependence on time, right? So what would be the value of my stock position, okay, at time t minus c? So let's assume that 0 is less than equal to t, less than equal to t minus c. Okay, I want to look at the value of my portfolio at x of t, at any point t where t is less than equal to t minus c. As I just said, this basically position is static, so our position is going to be 1 by RC 1 minus e to the power of minus RC, right? This is the number of units of stock that we were holding, and because it doesn't have any dependence on time, at time t, we'll be holding the same number of units, but at this time, the stock would be trading at ST. So this would be the value of my stock position, and I basically had borrowed this much money from the money market account, okay, and this would accrue interest at the rate of R, okay, it would accrue interest at the rate of R, so I need to multiply this by e to the power of RT, right? So this basically would be my position at time t. So this basically means that this is equal to e to the power of minus R t minus t, right? So at any time t, which is less than equal to t minus c, this is going to be the value of my portfolio. So what is the value of my portfolio when t is equal to t minus c? So x of t minus c is equal to, let's replace instead of t minus c. We'll get 1 by r c, 1 minus e to the power of minus r c. Instead of s of t, we're going to write s of t minus c. And here, we're going to have k e to the power of minus r, t minus c would give me minus rc. Okay, so this is one result, that the value of my portfolio at this point in time is going to be equal to this. Okay, because from 0 to t minus c, we were basically holding static number of shares of the underlying risky asset. So we could just basically easily compute the value of my portfolio at t minus c. Okay. Now, in order to basically compute the value of my portfolio at t, as you can see here, between t minus c and t, we basically need to keep changing the number of shares of the underlying risky asset that we hold, and the dynamics is basically governed by this differential equation. Okay. So now we can basically use number 4 to compute the value of my portfolio at time t. Okay, and that we can do by integrating both sides from t minus c to t. If we integrate both sides from t minus c to t, we'll be able to get the value of the portfolio at time capital T. So let's do that now. Let's call this result. This was number 4, so let's call this result 5. Okay, so this is the value of my portfolio at time t minus c. Now let's compute the value of the portfolio at time capital T. Okay, so now let's assume that our t minus c is less than equal to t, less than equal to t, and we basically want to figure out the value of the portfolio at time small t. Okay, when the small t is greater than t minus c and less than capital T. And we can do this by looking at our equation, the result 4, and integrating both sides. So this will go from t minus c to t, and here t is between t minus c and capital T, okay? And here we'll get d e to the power of r t minus u x of u, okay? This is equal to integral t minus c to t, small t, d e to the power of r t minus u gamma of u, s of u. Okay, and I have integral t minus c to t of e to the power of r t minus u, s of u, d gamma of u. Okay, so one thing to basically notice right now is when time is between t minus c and t, gamma t is given by this. So we can basically look at what is d gamma of t. D gamma of t is going to be given by 1 by rc, and here we're going to have minus e to the power of minus rt minus t, right? And you're going to get an r. So this r gets cancelled out and we'll get minus 1 by c e to the power of minus r t minus t, and there's a dt here, times dt. So d gamma of t is equal to minus 1 by c e to the power of minus r t minus t dt. So that we can substitute right here. Okay, so let's do all that. Let's basically solve this integral. So here we're going to get e to the power of r t minus t x of t minus e to the power of r. When I substitute instead of u t minus c, t gets cancelled, I'll get a c here, and x of t minus c. Okay, that's my left hand side. On the right hand side, if I integrate this, I'll get e to the power of r t minus t gamma t s of t, right? Minus, when I substitute instead of u t minus c, I'll get e to the power of r c gamma of t minus c s of t minus c, right? And I'm going to be left with this. Now if I put this here, I'll get minus integral t minus c to t e to the power of r t minus u s of u, and instead of d gamma of u, I'll put minus 1 by c e to the power of minus r t minus t minus u du. This, I have a plus rt minus u minus rt minus u. This basically goes to 1, and I'm basically left with e to the power of r t minus t x of t can be given by, now, e to the power of rc and x of t minus c. X of t minus c we just saw was our result number 5, right? The value of the portfolio at t minus c. That we can substitute right here. Here we'll get 1 by rc, 1 minus e to the power of minus rc times s of t minus c minus k e to the power of minus rc. Okay, that basically is that. Instead of x t minus c, basically I've substituted the value of the portfolio at time t minus c, which was equal to this. So that takes care of this term. Then I have plus e to the power of r t minus t. Now gamma t st. Now gamma t, I've already seen what my gamma t is. Gamma t when t is between t minus c and t is given right here. It's going to be 1 by rc, 1 minus e to the power of minus r t minus t. Okay, so that's my gamma t multiplied by st, right? That takes care of my second term. Then I have this minus e to the power of rc right here, gamma t minus c. Gamma t minus c would be what? Gamma t minus c again, when it's equal to t minus c, I'll get 1 by rc, 1 minus e to the power of minus rc. Okay? Minus rc. That basically is going to be my gamma t minus c. Then I'll have st minus c. That takes care of this term, and finally I have this term, which is minus minus would give me plus 1 by c integral t minus c to t s of u d of u. Okay, so now this term, we have a st minus c, this term, this term. So this is a negative, this is a positive, so this term cancels with this term, okay? And we have a ERC multiplying this thing, so we can write this as e to the power of r t minus t x of t is equal to, this would give me minus k, because we have a e to the power of minus rc here, multiplying by e to the power of positive rc, so that would basically become 1. I'll get minus k, and then I have this plus 1 by rc e to the power of r t minus t, 1 minus e to the power of minus r t minus t s of t, okay? And then I finally have this last integral t minus c to t s of u d of u, okay? Now I can divide both sides by e to the power of r t minus t, then I'll get x of t is equal to minus k times e to the power of minus r t minus t, right? And here I have r t minus t, divide this by this, so I'll get plus 1 by rc. This cancels out, 1 minus e to the power of minus r t minus t times st. That's my this term. And finally I'll get plus 1 by c e to the power of minus r t minus t integral t minus c to t s of u d of u. Okay, so that basically is what I'm going to get. Now in order to basically calculate the value of the portfolio at time capital T, all we need to do is T equals to capital T. So we'll get x of capital T, okay? When I put T equals to T, this becomes 0, so this becomes 1, so I get minus K, right? And here, when I put small t equals to capital T, this becomes 1, 1 minus 1 becomes 0, so this entire term goes away. And I'll get here, t is equal to t, so this basically becomes 0, this becomes 1, I'll get 1 by c, integral t minus c to t s of u d of u. Okay, and if you remember, what we wanted to prove was, as I said, that if we basically start with initial capital equals to this, and we at any point in time we hold this much amount of risky asset, then I wanted to show that the value of the portfolio at maturity is going to be this. Let's compare this with this, 1 by c integral t minus c to t s of u du minus k. That's exactly what I get here. Okay, so I've basically shown that if basically we start with this initial capital and we hold this much amount of stock at any point in time, then the value of the portfolio at time capital T is going to be equal to this. Okay, so all this math that we've done was just to basically show that this strategy actually works, and it basically gives us the value of the portfolio equals to this. Now we know that value of our option at T is basically nothing but max of 0 and x of t, right? We have to take the max of 0 and this. This we will denote by x plus of t. Okay? And now what we want to do next is we basically want to use a risk-neutral pricing formula. Okay? And basically figure out what the differential equation for our Asian option is. So we'll do that next. Okay, so now in order to calculate the value of Asian option, I can use the risk-neutral pricing formula. And as we know, risk-neutral pricing formula is given by Vt times e to the power of minus RT is equal to expected value under the risk neutral measure of V of capital T e to the power of minus R capital T given information at time t. Okay, I just showed you that Vt basically was equal to x plus of t, so we can substitute the value here and we'll get V of small t equals expected value under the risk neutral measure of e to the power of minus R t minus t x plus of t given information at time t. Okay? So now in order to basically calculate the right hand side, what I'm going to do is I'm going to define y of small t equals x of small t, which is the value of the portfolio at time t, divided by s of t, right? So yt, in other words, basically gives us the value of the portfolio in units of the risky asset. Okay, so this basically is the change of numeraire. What we're doing is basically we are changing the accounting unit. Earlier x of t basically was measured in terms of dollars. Now we basically are dividing it by s of t, so that would basically give us the value of the portfolio in terms of the in units of the risky asset, and that's denoted by y of t. Okay, so this basically is a change of numeraire. This can also be written as e to the power of minus r t times x of t whole divided by e to the power of minus rt s of t. So okay, I'm multiplying and dividing numerator and denominator by e to the power of minus rt. Now what I want to do is I want to figure out I want to take the differential of this dy of t. Now dy of t is basically nothing, so y of t is nothing but e to the power of minus rt x of t multiplied by e to the power of minus rt s of t to the power of minus 1. Okay, so what I want to do is in order to figure out the differential of this, I'm going to first figure out the differential of this, then I'm going to figure out what is the differential of this, and then I'll use those results to compute the differential of y of t. Okay, so let's first compute the differential of this. So differential of e to the power of minus rt times x of t is nothing but e to the power of minus rt, I'll have a minus r here, xt dt, and then plus I'll have e to the power of minus rt. What is dx of t? We just saw dx of t was given by gamma of t ds of t, okay, which is a change in the value of the portfolio coming from my stock position, and then xt minus gamma t st times r dt. This basically was a change coming from a money market account, right? So now we have a minus r e to the power of minus t x of t, and here we have positive xt r dt e to the power of minus rt. So this can cancel with this, and we basically are going to be left with e to the power of minus rt gamma t, and here I'll get d of st minus r times st dt, right? Now because this is modeled as stock is modeled as a geometric Brownian motion, we know that ds of t is equal to r st dt plus sigma st dw tilde of t. So from here we can see that this dst minus r st dt is equal to sigma st dw tilde t. So we can substitute that value here and we'll get d e to the power of minus rt x of t is equal to e to the power of minus rt gamma t sigma st dw tilde t. Okay, let's call that equation A. So in order to compute the differential of this, we already computed the differential of this. Now let's compute the differential of this particular term. Okay, so now we want to compute differential of d of e to the power of minus rt st to the power of minus 1, right? So this is going to be nothing but minus 1 by minus rt s of t whole square times d of minus RT S of t plus half times 2 divided by e to the power of minus RT S of t whole cube d e to the power of minus RT S of t d e to the minus RT. I'm just applying the E2's formula, and because we have a quadratic variation, we have these two terms that we're going to get. So now we haven't computed d e to the power of minus RT st, so let's compute that next. D e to the power of minus RT S of t is nothing but e to the power of minus RT. I'll get a minus R S of t dt plus e to the power of minus RT. ds of t is nothing but r st dt plus sigma s of t dw tilde of t, right? So here I have a minus r e to the power of minus RT st. I have a positive, so this term cancels with this, and here I'm going to get d of e to the power of minus r st is equal to sigma s of t e to the power of minus RT dw tilde of t. Okay, and this now I'm going to substitute right here, and I'll get the value of this. So d e to the power of minus RT S of t minus 1 is given by minus 1 by minus RT S of t square, and instead of this I'm going to substitute this sigma st e to the power of minus RT dw tilde of t, right? 2 cancels here, and I'll be getting e to the power of minus RT S of t cube, and instead of d to the power of minus RT st times the same, I'm gonna get sigma square st e to the power of minus RT square dt. Now I have e to the power of minus RT st right here, so this cancels with this. Here I have a square, so this cancels with this, and I'm left with minus sigma dw tilde of t plus sigma square dt whole divided by e to the power of minus RT st. This is my d e to the power of minus RT st 1. Okay, so let's call this, we had called this one equation A, so let's call this B, result B. Okay, now in order to compute this differential of y, okay, differential of this, we can use these two results A and B. So let's use that. So now differential of y of t can be written as differential of e to the power of minus RT x of t times e to the power of minus RT s of t to the power of minus 1. This is nothing but e to the power of minus RT xt d of e to the power of minus RT s of t to the minus 1 plus e to the power of minus RT st minus 1 times d e to the power of minus RT xt plus d e to the power of minus RT xt d e to the minus RT s of t. Okay, so I'm just applying E2's formula. Now basically let's substitute all the values here. E to the power of minus RT x of t, instead of d e to the power of minus RT s of minus t, s of t to the power of minus 1, I can basically use this result. This is nothing but there are sigmas on both the sides, so I can take out one sigma here. I'll get sigma dt minus dw tilde t. That's my numerator. Denominator is going to be e to the power of minus RT st, right? That's the first term. Second term, I'll get e to the power of minus RT S of t, d to the power of minus rt times x of t is given right here. That's e to the power of minus rt gamma of t sigma st dw tilde t, right? And finally I have this multiplied by this, which is nothing but this is my sigma times sigma dt minus dw tilde of t by e to the power of minus rt st, okay, times e to the power of minus rt gamma t sigma st dw tilde t. Okay, so here I see this cancels out with this. Xt by st is nothing but y of t. This is y of t times sigma, because I have a sigma here, then sigma dt minus dw tilde t. Okay, this cancels out with this st cancels out with this, so I have sigma gamma t dw tilde of t. So that's my second term, and this cancels out with this cancels out with this. So here I have sigma square, because I have a sigma here, that makes a sigma square, gamma of t dw tilde of t, right? Gamma t, and then inside the brackets I have sigma dt minus dw tilde of t. So now let's solve this further. This is nothing but yt times sigma and sigma dt minus dw tilde of t. That's my first term. I'm writing it as is. My second term was sigma gamma t dw tilde t. That also I'm writing as is. Now multiplying this inside, I'll get a dw dt term which is going to go to 0. So I don't need to worry about it. And I'll get a dw term which is going to be dt. So I'll get minus, because I have a minus here, sigma square gamma t, and dw will become dt, right? Now what I can do is I can combine these two terms, and this is nothing but y of t sigma dt minus dw tilde t. And here if I take sigma gamma t outside the brackets, I'll get dw tilde t minus sigma dt, right? And here what I can do is I can now take out dw tilde t minus sigma dt, and I'll be left with, if I take this out, I'll be left with, and a sigma I take out, I'll be left with gamma t and minus y of t, right? So if I've taken this out and a sigma out, I'll get gamma t, and here I'll get a minus yt. So this is basically my d of y. Okay, so just basic manipulation I've done. I mean, all I've done is basically first, in order to compute this dy of t, I needed to figure out the differential of this and differential of this, which I computed in result a and b, right? Then I used Ito's formula to basically calculate this differential, and I got this. Now when you see dy, we have a dt term here in dy, okay? So this is not really a martingale under p tilde. So dy is not a martingale, so y is not a martingale, under p tilde, okay? Because we have a dt term here. So what I'm going to do is now I'm going to basically use Girsanov's theorem, and I'm going to change the measure, okay? And under the new measure, I'm going to make this as a martingale, Okay, so that's what I want to do now. I want to basically change the measure using Girsanov's theorem, and let's see what happens then. Okay. Okay, so if you remember when we talked about Girsanov's theorem, that time we had defined a Redon-Nikodym derivative as z of t is equal to the power of minus integral 0 to t theta of u dw of u minus integral 0 to t theta square u du, right? And then we basically had defined a process w tilde of t as w of t plus integral 0 to t theta of u d of u, and in differential term we can write this as dw tilde of t as dw of t plus theta t dt, right? And then we said basically we're going to define a new probability measure given by p tilde, and this p tilde would be defined in a way that this p tilde of a would be integral over a z of omega dp of omega, right? Where z of omega we said was equal to z of capital T. And if we change the measure according to this formula, then we said that under this new probability measure, w tilde of t would basically be a Brownian motion. Okay, so something similar is happening here now. Instead of, so here we can basically write dw hat of t as dw tilde of t minus sigma dt, right? And if we compare these two, we basically are defining a new process, w hat of t, and instead of theta of t, from here we can see theta of t is nothing but minus sigma. Okay, so if we define theta of t as minus sigma and we compute the Redon-Nikodym derivative as minus integral theta is minus this sigma, so this is, and integral 0 to t of, now in our world we already are working under w tilde, so for us we basically are going to define, this is going to be w tilde, so we'll get w tilde of t, right, and minus integral theta square is going to be sigma square times t. Okay, so if you now define Redon-Nikodym derivative as z of t equals this, okay, then z of capital T would be just basically small t replaced by a capital T. Then basically under this, and if we define a new probability measure, p hat of a is equal to integral over a z of omega dp tilde of omega. Okay, then under p tilde, this new process w hat would be a Brownian motion. Okay, so what we're doing is basically we're applying Girsanov's theorem here, and we're basically changing the measure. We define a new probability measure p hat, and under p hat, if you use this as the Redon-Nikodym derivative with small t replaced by capital T, then we basically get w hat of t as a Brownian motion, right? And we can basically substitute that here. So then in that case we'll get dy of t is equal to gamma of t minus y of t, and okay, and we have a sigma here, let's not forget the sigma, and this would just be dw hat of t, right? Because that's how we define dw hat of t as equal to this, so this becomes dw hat of t, and as I said, under p hat of t, this basically is a Brownian motion. So now we see that under the new measure, the differential of y doesn't have a dt term, it only has a dw term. Hence, this basically y is a martingale under the new probability measure. Understood? So now that was an important thing to note, and z of t can also be written as z of t, as I said, is exponent sigma w tilde of t minus, sorry, there is a half, okay, minus half sigma square t, right? And we know that st is nothing but s0 x to the power of sigma w tilde of t minus half minus r plus r minus half sigma square t. Okay, from here we can basically see that st by s0 is nothing but sigma w tilde of t minus half sigma square t times e to the power of rt, or this basically is nothing but my z of t. So z of t can also be written as s of t by s0 e to the power of minus rt. Okay, so this is something that we're going to use in just a moment. So right now what is important to understand was we basically computed the differential of y. Okay, and that time we saw that under p tilde we were getting a dt term. Okay, hence this was not, y was not a martingale under p tilde. So we, in order to make it a martingale, we basically changed the measure using Girsonov's theorem. Okay, and we basically defined a Redon-Nikodym derivative. We defined a new process. Okay, and here theta of t was equal to minus sigma, and we defined Redon-Nikodym derivative as this. And we then defined a new probability measure given by p hat. And as I said, using Redon-Nikodym derivative, we said that under p hat, this w hat of t was a Brownian motion. So if that was a Brownian motion, then we basically replaced this by dw hat of t. So now we basically saw that under p tilde, this w hat of t was a Brownian motion, and we don't have a dt term here. That basically means that y of t is a martingale, under p hat. Okay, it was not a martingale under p tilde, but under p hat it's a martingale. Okay, now we're going to use this to basically compute the differential equation. So let's see how that is done. Okay, so in order to compute the differential equation, you can basically use the risk neutral pricing formula. We know that v of t is given by expected value under the risk neutral measure e to the power of minus r t minus t x plus of t given information at time t. Now this notation basically meant this is nothing but max of 0 and x of t, right? And this can also be written as, we can multiply and divide this by s of t, but this will basically become max of 0 x of t by s of t. Okay, so we're dividing this by s of t and we're multiplying this by s of t, so basically this becomes s of capital T, and this basically is y of capital T, so this becomes y plus of capital T, right? And we just saw that z of t is given by this formula. So z of capital T can be written as s of capital T by s0 e to the power of minus r capital T. And z of small t can be written as s of t by s0 minus rt. So z of capital T by z of small t would be s of t by s of small t minus rt minus t, right? From here we can see s of t basically is then given by 1 by e to the power of minus rt minus t, okay, times s of t times z of t by z of small t, right, which we can basically substitute right here. So this becomes, so x plus of t, this basically becomes 1 by minus rt minus t st z of t by z of small t times y plus of t. Now we can substitute this right here in this expectation, and we will get v of t is then given by expected value under the risk neutral measure. Now we have e to the power of minus rt minus t and divided by this, so this two would cancel out, and we'll get st times z capital T by z of small t, right, times y plus of t given information at time t. Now we can take out what's known. So this basically is s of small t and z of small t are known at time t, so we can take that out of expectation. So we'll get v of t is equal to s of t divided by z of t, expected value on the risk neutral measure. These two we are taking out, so we'll get z of capital T times y plus t given information at time t. Now, if you remember when we were talking about Redon-Nikodym derivatives and change of measure, we basically saw that this entire thing, 1 by z of t, expected value under the risk neutral measure of this is nothing but, we can use change of measure, right? So this basically v of t can be written as s of t. Now here this would be expected value under a new probability measure p hat, right? Expected value under p hat and this would be y plus of t given information at time t. So we basically have used the Redon-Nikodym derivative to change the measure, and when we do that, the expectation basically gets computed like that. Okay, so this is basically our expectation. Now one thing to notice here is, as I just we just talked about, under p hat we said y of t was a martingale. Not only a martingale, if you look at the stochastic differential equation for y of t under p hat, on the right hand side you see that the source of randomness is either the Brownian motion or it's the process itself. There is no other source of randomness, and we've talked about this earlier, that if on the right hand side the only source of randomness is either the Brownian motion or the process itself, then the solution to that stochastic differential equation would be a Markov, right? So y of t is also a Markov. Okay? And since it's a Markov under p hat, we can basically write this expectation y plus of t as a function of time and y of t, right? Since it's a Markov under p hat, we basically, you remember the Markov property, right? That there exists a function g such that basically this can be expressed as a function of time and the process at time t. Okay, this basically comes from the Markov property. So this is important, that this expectation can be written as a function of t and y of t. Now what I want to show you is that this expectation, so if I say x of t is equal to e hat of y plus of t given information at time t, then I want to show that this x of t is a martingale, that this basically is a martingale. And it's easy to see why. What is the martingale property? That e hat of x of t given information at time s is equal to x of s. And from here we can see x of t is nothing but this. And if I put a conditional expectation f of s on that, I can use iterated conditioning and I'll get that equal to x of s. So this basically expectation is a martingale. Okay, and this expectation is represented by this function, right? Now, if this is a martingale, then I should be able to take the differential of this and set the dt term equals to 0, because if it's a martingale then we should not be having a dt term. Okay, so again this expectation basically is a martingale, and we can see that by substituting x of t equals to this and then basically taking expectation given information at time s, and we'll see that using iterated conditioning this becomes x of s. Hence this expectation is a martingale. So now because this expectation is equal to this function, we can take the differential of this function. Okay, and when we take the differential of this function, we'll get a dt term and we'll set that to 0, and that way we'll get our differential, the partial differential equation. So let's do that now. We basically we want to take the differential of this dg of t and say y. Okay, we want to take a differential of this. I'm putting a dummy variable y, so we will get g of t dt plus g of y dy plus half g of yy dy dy, right? G of, so this basically becomes g of t dt. What is dy? Dy we just saw was this, right? So g of y, and instead of dy I'll put sigma gamma t minus y of t dw hat of t plus half g of yy. dy would be sigma square gamma t minus y, instead of y of t, sorry, I'm going to be using a dummy variable here, y, this square, okay, and dw would be dt, right? So now basically I can combine these two dt terms and basically set them to 0, and I'll get my partial differential equation. Okay, so basically let me combine this. Now the dt terms are given by g of t, which is a dt term. Then I have half g of yy sigma square gamma of t minus y whole square. Okay, this basically is my dt term. And then I have a dw term, which I'm not going to write here. There's going to be a dw hat term. But I need to substitute this dt term equals to 0, because we basically are taking differential of a martingale, and that should not have a dt term. So we'll get this partial differential equation. Okay, where g basically, I just haven't written the arguments of this function, but basically it's a function of t and y. Okay, so this basically is our partial differential equation for this function, and we just saw that once we basically get, I'll just show you the boundary conditions, but once we basically compute the function, we basically, in order to compute the value of the Asian option, we basically need to substitute that function right here. So we'll get v of t is equal to s of t times that function. Okay, because this whole expectation was given by this function, so we just need to replace that here, and we'll get the value of our Asian option. Now what are the boundary conditions here? Now boundary conditions, basically g of t comma y, okay, limit as y goes to minus infinity. So g comma this, if y goes to minus infinity, okay, that basically means that y of t basically goes to minus infinity. Then basically what's going to happen is, even at, if y basically goes to minus infinity at time t, with almost probability 1, even y of capital T would go to 0. Because if it's going to minus infinity, what are the chances that it's going to be able to get back into a positive territory? It's almost 0. So y of t is going to be 0, and if y of capital E is going to be 0, and if y of capital E is going to be 0, then if y of t is going to be negative, because if this is minus infinity, then y of t with almost probability 1 is going to be negative. In that case, y plus of t would be equal to 0. And if that's the case, then basically, as you saw, our expectation, this basically is going to be 0. The value of our option is, the function is going to be equal to 0, and this expectation is going to be equal to 0, right? So this basically becomes equal to 0. Understood? If y basically goes to 0 at time t, then basically with probability almost 1, we basically will have y of t going to will be negative, and y plus of t would be equal to 0, and this function, this expectation would be equal to 0. So that's the first boundary condition. Now similarly, the second boundary condition is limit if y goes to positive infinity at g of t comma y at some point in time. If basically y goes to plus infinity minus y, this basically is equal to 0. And why is that the case? When at time t y goes to plus infinity, then we can drop this max of 0 and y of t, right? Because if it's going to positive infinity, then chances are, the almost probability 1, it's going to end up positive. If it's going to end up positive, then we can drop this max of 0 and y of t because it's going to be positive anyways. So then this expectation basically becomes expected value, instead of y plus of t, it will be y of t, right? And y of t, the expectation of y of t given information at time t. Now this basically, as I said, this is also a martingale, so this would just be y of t, which in our case is equal to y, right? So this basically becomes y, and y minus y is equal to 0. Okay, so that basically is our second boundary condition. Okay, so this is the first boundary condition, this is the second boundary condition, and this basically is the differential equation that we were looking for pricing of a Asian option. Okay, so that was a lot of theory. Hopefully this discussion was clear. We basically used change of numeraire to compute this partial differential equation, and I showed you the boundary conditions for this. Once we basically solve for this function, we basically need to substitute it here. This basically is nothing but our function g. So v of t then basically would be s of t times function g t of y of t. Okay, and we'll get our value of Asian option. Okay guys, so that's all I wanted to talk about today. Hopefully the discussion was clear. That kind of concludes our discussion on exotic options. So I'll see you guys next time. Bye.